This is Unit 8, Video 10. In this series of videos, we will talk about acids and bases, which essentially refer to a very important class of reactions that occur in solution. So acids and bases, as you'll see, are usually related to aqueous solutions, meaning substances dissolved in water. So let's put together some definitions. The first definition of an acid and a base is the Arrhenius definition. There are actually a few of them that we'll discuss. Arrhenius is the most basic definition of the two. An acid, according to this definition, is a substance, chemical substance, that when dissolved in water, notice the relationship, connection to water, increases the concentration of hydrogen ions. These are H+ ions. Whereas a base is a substance that, dissolved in water, increases the concentration of hydroxide ions, OH-. Now you can notice that an H+ ion and an OH- ion together form water, HOH. So these are actually centered around water. And so these are the basic definitions of an acid and a base. Let's talk about some properties. Since acids produce H+ in solution, to the taste, there have been some taste tests done, and acids taste sour. In fact, the classical example of this is a lemon, which contains ascorbic acid, and many citrus fruit, and not only ascorbic acid, also citric acid. Citric acid is the main component. Ascorbic acid is also in there, but citric acid. But if you take a taste of HCl, which we would not recommend, it also will taste sour. These are electrolytes in solution, which means they break apart to conduct electricity. The electrolytes can be weak or strong, depending if the acid itself is weak or strong. To the feel, to the touch, they actually feel like water. So, before they begin dissolving away your skin, they will feel like there's just water on them. But they react with metals, not only with skin, but with metals. And they also react with carbonates, which contain CO3 carbonate ion, and that releases CO2 gas. So carbonates are actually organically deposited source of carbon, which can be released if you put an acid to it. Now let's talk about this H+ that forms from an acid. The H+, the hydrogen ion, is technically just a proton. So being a proton, so this guy here is just a proton. The reason it's a proton is because hydrogen is the first element on the periodic table, and once you lose the electron, you just remain a proton, and there are no neutrons, remember, in hydrogen, since hydrogen's mass is 101, so all you have is that proton. And it's very unstable in water. A tiny little proton is unstable, so it will team up with another water molecule to produce this species called a hydronium ion. It's actually one of the few positively charged polyatomic ions that we discussed, the hydronium ion. And here is the visual representation of it. A water molecule teams up with a proton to give you this hydronium ion. Hydronium is actually much more stable in water, and that's what most acids exist as. Now, the acid can be monoprotic. So this word protic is actually referring to the proton. Monoprotic means you have one hydrogen that can ionize, that can be removed. A ditriprotic acid has 2 or 3. So sulfuric acid, for example, has 2 hydrogens that can be removed. Phosphoric has 3 hydrogens that can be removed. Now, this is not to be confused with is it a strong or a weak acid? Turns out that phosphoric is actually a weak acid, whereas sulfuric is a strong acid. So this doesn't represent strength, it represents how many hydrogens can come off of it. Some more properties. Most acids will start with the formula H, the way they're written. They turn litmus paper, which is an indicator, red. So you've heard about the litmus test for something. That means there's a quick test whether it's an acid or a base, whether it's this or that, and acids turn litmus paper red. Another famous indicator that we will definitely use in lab is phenolphthalein, and that is clear in an acid. It'll be a different color in a base, as we'll see. And these indicators, which are the acid-base indicators, there are actually thousands of them. They themselves are actually weak acids. So litmus paper, for example, this is litmus paper, is soaked in an acid. Essentially it's a solid acid, and then that acid itself is reacting with the acidity in the water, turning red if it's an acid, and it'll be blue if it's a base. So these indicators are actually weak acids, and they do the same thing as an acid does. They lose an H+. Let's go through some common acids that you have heard of, played with in the laboratory, and we will use some more. So hydrochloric acid is the most famous acid in the chemistry laboratory. Everyone's heard of it. But interestingly enough, this is actually the same acid that you carry with you at all times. It's the acid found in your stomach. It's the acid that helps break down food. It helps to make sure your food, all the bacteria is killed in it before you absorb it and so forth. So this also has a common name, a street name, as we say, muriatic acid. The word actually comes from the word salt pertaining to salts, muriatic acid. So you can actually go to your Home Depot, local Home Depot store, and pick up a gallon or so of muriatic acid. Be very careful. It is as dangerous as it is in the laboratory. Sulfuric acid is the second one that folks usually learn about. And this acid is extremely important industrially. Well, first of all, it's used in car batteries. So every car battery actually is filled with sulfuric acid. It's the electrolyte used in car batteries. It's heavily used in chemical synthesis, whether of organic substances, medicines, or metals. Extremely important in forming compounds in the laboratory. It's actually a famous catalyst, very famous catalyst in syntheses. Now, in fact, it's so important in chemical syntheses that industrially, it's the acid that ranks as the top substance that you can use to gauge your industrial activity. In fact, a country's wealth and industrial activity can be gauged, can be measured by how much sulfuric acid it uses. It's extremely important. So there's sulfuric acid. Nitric acid is usually the third one. And this acid is also pretty important to make, synthesized substances, most famously explosives. We definitely need explosives in our not only for war, machinery and so forth, but actually to develop the country. If you want to blast away a part of a mountain to maybe extract some sort of ore, or just build a road, so it's actually used for blasting, so for peaceful purposes. Explosives famously use nitric acid, and then making rubber, plastics, and many other things. So nitric acid is also very important. Phosphoric acid is actually found in soft drinks. Many drinks actually contain phosphoric acid. Here it is, as a flavoring agent. It's also used in industrially many applications. You can actually remove rust from metal with it. The PO4, the phosphate portion of it, is actually in our DNA, in the backbone of DNA. Phosphoric acid is important. Carbonic acid is dissolved CO2, which forms in water. Carbonic acid, H2CO3. This acid gives soda the bite that you feel whenever you drink soda. It also acts as a buffer in our bodies. So this acid also is found in our bodies. There are two of them so far that we've, three of them actually, that are found in our bodies. If you think of phosphoric acid as the phosphate. Acetic acid is found in vinegar. This is the vinegar acid, probably the most famous organic acid. In other words, acid that comes from a plant material and is used by humans. So everyone has a few gallons, maybe a gallon or so, of vinegar at their house. And it's actually related to ethanol. Ethanol is actually the same formula except without one oxygen. If you remove one of the oxygens and actually add another hydrogen to make it an ol, you get yourself ethanol. So ethanol, if you keep fermenting it, if you keep reacting, it actually becomes acetic acid. Another name for acetic acid, actually the organic name for acetic acid is ethanoic acid. And that's how we call acetic acid in the organic laboratory, ethanoic acid. Okay, so we have binary acids. We can essentially make two categories of acids. Binary. Binary just means made of two elements, hydrogen, and then some sort of nonmetal. So hydrochloric acid, hydrobromic acid, hydrosulfuric acid. And to name these, you have to put the hydro in front. That was the naming convention. If you remember, we went through naming of these acids in a previous chapter, first semester actually. So hydro, and then the nonmetal, and then put ic and acid. So hydrochloric acid. The other category are oxyacids. These are made from polyatomic ions. and they contain oxygen in them, so famously nitric acid, sulfuric acid. To name them, you have to know the polyatomic name, and then the polyatomic name gets appended with ic, and then put acid. Notice there's no hydro here. The hydro, no hydro, is missing, and that's the difference between the naming of the two acids. You can also use -ose for the ending if it's an ite. If you remember, polyatomic ions that end in ate, like nitrate, become ic, like nitric acid. Nitrite becomes nitrose acid, and we'll actually review these. So this is a review of the naming rules. In this chapter, we want you to be able to name these acids, and this is a sort of a review toward the end of the year of the concepts we talked about first semester. So you have to review your polyatomic ion chart. Now, we won't require you to remember too many of these, but definitely the most common ones. So for example, nitrate, this is where nitric acid comes from. Carbonate, this is where carbonic acid comes from. Sulfate, for sulfuric acid. Phosphate, for phosphoric acid. And then if you remember that ate and ite are actually related by one less oxygen. So if you know your ate, if you know your nitrate, you can actually get rid of one of the oxygens, the charge stays the same, and you get nitrite. And nitrite then can become nitrose acid. If you put a hydrogen on one of these polyatomics, you can call it hydrogen carbonate, also called bicarbonate. And these are the halogens-based oxyacids. So if you have chlorate, remember chlorate is connected to chlorite, one less oxygen, to hypochlorite, two less oxygens, or to perchlorate with one more oxygen. And the only difference here, if you know these names, you can simply call this, if you put an H on this, this is called perchloric acid. If you put an H on here, this is called chlorose acid. And the same thing happens with bromine and iodine with the polyatomics. So review this, and let's do some practice. Before we do some practice, let me also remind you of the T43. Remember we talked about the T43, and this is a way of memorizing polyatomic ions based on technetium 43 is what we came up with. So the T is referring to the number 3, so 3 for 3. So all of these, boron, carbon, nitrogen, will have 3 oxygens, so it'll be O3 for all of these. The ones that have a 4 will have an O4, and then back to these guys here will also have an O3. That's the idea. Now the charges, remember, go like this. You have a -3, a -2, and a -1, and then it restarts here, a -3, a -2, and a -1. So for example, if you have, let's take a tough one, let's do arsenic acid. If you have arsenic acid, or rather arsenate, let's begin with arsenate. You got arsenate, the polyatomic arsenate, well, that's arsenic with, let's see, 4 oxygens, because it's on the 4, and a -3 charge, because it's in that group. So this would be arsenate, which then becomes arsenic acid. And these refer to the 8s. So, for example, boron, this would be borate, referring to borate. Iodine, referring to iodate. There is such a thing as iodite, hypoiodite, so all of these can actually be derived from that. So let's try a few of these. See if you remember how to name acids. So the first one is HI, and this is a binary acid, which means we need the hydro. We need hydro in binary, we don't need them in the oxy. So in this case, you'd say hydro, iodic, and then acid. Iodic acid by itself would be the polyatomic based one, so you make sure you put hydro in front. So this is good old nitrate. So if you recognize this as the nitrate polyatomic ion, then this becomes nitric acid. The nitrite polyatomic ion, ite, becomes ose, so you have nitrose acid. So here we have, is this chlorate? Nope, it's perchlorate. Being perchlorate, because you have one more oxygen than the chlorate, you get yourself chloric acid. This is the famous one that's different from hydrochloric. So hydrochloric would be HCl. This would be hydrochloric acid. Just chloric acid would be the polyatomic version. And then this is from chlorate down to chlorite, and then down to hypochlorite. So this is actually be hypo hypochlorous acid. Hypochlorous acid. And notice no hydros for any of these. These are oxyacids. And then we're down to H2S, which then is back to the binary acid. So we'll call this hydrosulfuric acid. Now notice that this substance here is usually referred to as just hydrogen sulfide or dihydrogen sulfide as a gas. It's actually a famous reactant in its own right. But if you put it in water, if it becomes an acid, then we call it hydrosulfuric acid. The idea is this substance becomes an acid because of its relationship with water. Alright, so we'll stop video 10 here and continue on in the next video.